Welcome to another episode of Code for Thought. And my guest for this episode is Duncan McGregor. A number of years ago, Duncan and I worked together at a company in Basingstoke, and if you're wondering where that is, it's about 50 miles west of London. This was my first job as a software engineer in the private sector, and yes, we are talking a really long time ago now, and as such quite a culture shock to go from academia and developing software to support some research to an actual full-on production of software. At the time I met Duncan, he already has been working in the industry as a freelancer for some time, and it was through him that I first learned things like pair programming, test-driven development, and some of the agile software development practices. So I was very pleased when we bumped into each other again last year in 2024, when I discovered that Duncan actually has a YouTube channel where he talks about programming. And I already had Duncan as a guest for one of the bite-sized RSE episodes. Given Duncan's experience, however, I thought it's worth our while to talk to Duncan for a full episode. And in fact, we spent almost half of our conversation talking about going from research software to production code. But we actually started with something else. A project Duncan and a colleague of his did at the Met Office in the UK last year, in particular one aspect of it, as Duncan will explain in a minute. That is, how he can organize efficient computation of huge datasets when the data are spread over different data centers. And so, without further ado, let's go straight into it. Hello, Duncan again.
Hello, Peter. It's lovely to be here.
Yeah, well, thank you very much. It's lovely to have you here. And you already went on the show on a bite-sized RSE session last season. I think it was on Python packaging or something like that. I honestly should remember, but I can't.
Approvals testing, I think. I was there.
Yes, it was testing. Obviously, I cut this out. Or maybe not, so because I think memory lapses are worth recording too. But could you quickly introduce yourself again, please?
So, hello, I'm Duncan. I'm a professional software developer, largely on the JVM these days, a language called Kotlin, which is kind of like Java. I was a trained physicist at one point, but really have made my living as a professional software developer for 30-some years, and I'm now pretty much retired, just running a YouTube channel showing people how I think they should program computers.
Indeed, exactly. And the YouTube channel, I think, was programming with Kotlin, but it's now rebranded, isn't it?
It was refactoring to Kotlin, and it's now pairing with Duncan.
Okay. So independent of Kotlin and independent of programming languages.
I think it's still largely Kotlin, to be honest with you, because that's what gives me joy.
That probably makes for another episode, because what we want to talk about, one thing we want to talk about is your project at the Met Office that you had. And could you quickly describe what this project actually was?
So climate science and the Met Office, obviously part of climate science, it's, for those who don't know, it's not short for Meteorological Office, but it was the Meteorological Office at the UK government, and it's now just the Met Office. They have a problem, and that's huge amounts of data. For example, 2.8 gigabytes is the output for the Met Office's MOGREPS model for air pressure predictions, just that one thing. And so we are producing loads and loads of data as both predictions and measurements of climate, and we need to process it somehow. Mm-hmm. The problem with lots and lots of data is that it has to live somewhere. So say I wanted to process 10 days of air pressure predictions on my local computer. Then I'd have to download 30 gigabytes onto my local computer. Yeah. If I wanted to try and find the correlation between air pressure and temperature, I'm sure that's the thing. I'm not sure it's a thing that climate scientists want to do. But if I want to do that, it would be 60 gigabytes, and that's just for one run. Then we have the problem of running computations on that amount of data. So once we've got that amount of data, we want to be able to throw lots of compute at it. In order to get our results quickly.
And also that includes parallel computing because, the Met Office is using supercomputers.
So the Met Office is using supercomputers, which are, as you say, parallel and these days largely distributed. But I think the problem is less the problem that the Met Office has because they live in their own sort of world, but the problem is more what users of the data that they are producing have, because the Met Office is publishing its data into AWS, for example, but in Europe, where you might be a researcher in the United States.
Mm.
And if you're a researcher in the United States, then obviously it's slower to download this 60 gigabytes onto your machine. There is a solution to that, which is to move your compute to the place that the data is.
Yeah.
So I was contracted by the Met Office to look at this concept of data proximate compute. How do we move the computation to where the data is?
Yeah.
And that's reasonably simple if your data is just in one place, but gets a lot more complicated if your data is in more than one place.
As is the case in this one.
Yes. So, for example, we might be comparing the output of a Met Office model the output of which is living in Europe with NOAA data in the United States, for example. And if you've got two big data sets, one in Europe, one in the United States, where do you put your computation? Well, you either move 30 gigabytes one way or you move 30 gigabytes the other way. Neither of those is palatable. So the project that I worked on used technology called Dask. I don't know whether Dask is a well-known thing.
Maybe to some people, but I'm not familiar with it. So maybe you should explain it just for my benefit.
So I like to think of Dask as distributed pandas and NumPy.
Right.
So pandas, as I understand it, I'm not really a Python programmer, is a sort of data set abstraction. So it allows you to load up big data sets, look at what measurements they are referring to, slice and dice them, multidimensional arrays, those sort of things. And so Dask effectively allows you to write pandas and NumPy code, but run it on other machines.
Okay.
And you can either do that running the code on your own machine, distributing it across processors on your local machine, but more usefully, maybe you can set up a cluster of remote workers, processes, actual physical machines, whatever, and then Dask will distribute a workload amongst those workers. So normally you would run up a Kubernetes cluster that would have compute somewhere, say in a data center, and then you run up Dask. Dask has a sort of scheduler, and then your pandas and NumPy code is distributed amongst the processors running in the cluster.
All right. Okay.
And it's sort of the scheduler's job to work out which workers have capacity and send tasks to them. And those tasks are largely just Python code. So you write Python, maybe even just in a notebook, and it sends the serialized Python bytecode off to those machines and says, okay, you work on that.
Did it work straight out of the box then?
Dask does work straight out of the box, and just for parallelizing jobs even on your local machine is very useful, very easy. But there are sort of two ways to look at it. One is I want to parallelize, say I've got 100 files worth of data and I want to process those in parallel. That's one way of parallelizing a thing. But the other way that Dask parallelizes things is chunks. So you can say I've got this large data frame, and so instead of having 100 of them, I've got something that's 100 times larger. And so I could take that data set, move it into chunks, and then send those chunks off for processing on workers. And there are file formats like netcdf and zar that support this chunking idea, so that workers can say, okay, my job is to average this n-dimensional array between this bound and this bound and spit out the answer. And then somebody else's job is to average this other chunk of this n-dimensional array and spit out the answer, and somebody else's job. And then you bring those all things together in the scheduler and it will say, okay, now I can build another n-dimensional array out of these averages. So the scheduler is a really clever bit. Its job is to distribute these tasks and then ask workers to exchange data so that it can finally sort of get whatever answer you want back.
Yeah.
Reduce our 600 gigabytes to, the answer 7 or something.
Which is more manageable, obviously.
Which is more manageable. We like 7, yes. Sometimes we like yes or no.
Indeed.
So a cluster is normally in one place. If I was processing Met Office data, I might like to say, well, I want to run up a cluster in the AWS data center that is holding the Met Office data. That way I don't have to send much data in and out of data centers because that's expensive and slow. So normally a cluster is one place where the data is, and the data is accessible to all the machines in the cluster. But say we have 60 gigabytes in one data center, 60 gigabytes in another data center. We wanted to say compare the averages or some
Between
reduction of those two things. What we'd like to be able to do is split a cluster into some workers in the place where some data is and some workers in the place where the other data is, and then have something automatically work everything out. So we don't want to move the data to just one place. We want to do the reduction in the place where the data is, and then combine those reductions once the data is smaller on some set of workers. And Dask, it turns out, can do this sort of thing.
But
well,
I feel a but
not even a but, really. I mean, Well, I mean, I think the clever thing was that we realized that Dask workers could be labeled. So Dask has this idea of labeling a worker. That's the thing that you do in the compute. And that was normally used for things like whether it had a GPU or an amount of RAM and so on. So you could say, I want to send this job only to workers that have a GPU.
All right. Okay.
And then the scheduler would say, okay, well, I understand that. So it would sort of like tag tasks with where they could be run. What we realized, though, was that you could use a label as to label a location. So you could say, oh, well, this data is only available in this place, and these workers are in this place as well. And if you do that, then you could tell the scheduler, okay, go and make this computation. It would say, well, hold on, I have this EU label, for example, that says that these tasks can only be run on something that is EU, and that means they have access to data locally.
Right. So the EU being sort of one of the regions in Amazon.
One of the regions, exactly. We treat the location of the data and the location of the worker that will be able to run that data as a property, as a label. It turns out it wasn't quite that simple because Dask also has sort of work stealing.
What does that mean?
So the labeling was there to prefer workers rather than insist on workers.
Right. Okay.
And if a worker becomes idle, then Dask by default will say, well, you may not have the label, you may not have the GPU or the amount of RAM, or it turns out be in the place for this data to be able to see this data. But I'm going to give this job to you anyway because I'd rather you weren't sitting around doing nothing.
Okay.
That turns out to be horrendously inefficient if it means you copy 60 gigabytes across, from one data center to the other.
Yeah.
And so we've, with the help of some of the Dask developers, found a way to stop that work stealing happening effectively.
Oh, right. Okay. So you worked with the people from Dask themselves.
Yes, it was very helpful. Yes, in the end, we came up with a system, sort of lots of cooperation. It was the Met Office and the European Weather Cloud, which is ECMWF and EUMETSAT, as I say, work with Dask in particular, to come up with this system that runs up a WireGuard network, which is a way of running a sort of virtual network to allow all these workers in different data centers to see each other, because otherwise normally security would mean that some machines couldn't see each other. So we end up with this flat network. I mean, the results were really quite promising. Amazon have themselves, I'll make sure you get linked to it, published a paper for using this sort of technique in their data centers, using their own sort of proprietary sort of technologies.
Yeah. Is that because of the work that you've done for the Met Office? Is that something that has now been, do I understand this right? Something that is now being adopted by Amazon as a way of dealing with that?
Yes. So there's an AWS Solutions library, distributed compute on AWS with cross-regional Dask. There's also a write-up on GitHub and on the Dask blog of how to make these things work.
So what made you choose Dask in the first place? Is Dask the only way to schedule tasks? Or
there are other technologies. I think Spark is one, but Dask has sort of been taken to heart by climate scientists, I think. In particular, it sort of forms the basis of some sort of toolkits. One's called Pangeo, where people are saying, well, what technologies are we finding useful? Yeah. And then packaging together Dask and something called Xarray and data formats and so on, and saying, okay, these are the technologies we expect to be part of the solution to the problems that we have.
So it was kind of the remit that you had, so to work within the Dask environment. Is that
actually, the Met Office were very open to any solutions, but when we looked at what people were actually doing, that seemed to be a really good starting point.
And ZAR as well, was that sort of part of the package? Because you mentioned
yes, ZAR is a really interesting multi-dimensional data set format that allows you to split data sets across effectively cloud object storage. So you can take chunks of data, you can build a ZAR file that says the data for these dimensions of this data set, these partitions of this data set is sitting in this object file, which is an S3 or whatever your cloud storage provider provides. And that then provides the sort of low-level facilities so that you think you're just reading from one file, but actually what's happening is that you're reading from multiple files.
And again, like Dask, my question with Dask, if there are any alternatives, are there any alternatives to ZAR? And what made you choose ZAR then?
Actually, we didn't choose ZAR so much as show that these things work. I think NetCDF is the name of the sort of standard file system, the file format for meteorological data, but I'm afraid I'm a humble not scientist, so I don't really know.
Well, not quite non-scientist. You did physics.
And not quite humble, to be true.
Not quite humble either. Moving on swiftly from that one. So how did Met Office then respond to your solution? So, I mean, Amazon were quite happy because they included it in their AWS library, but how did the Met Office respond to that?
To be honest with you, I don't know where this work has gone. It was a short-term sort of study contract for me. And my sponsor from the Met Office moved on, so quite how much this has been adopted, I don't know.
Well, as Duncan said, we don't know how far this technique went at the Met Office, but Amazon have adopted it though. And you can find the links and technical paper of what Duncan, his colleague on the project, and the team at Dask did in the show notes. A quick word about the Met Office before we go on. Duncan and I didn't spend that much time talking about the work that's happening there, apart from the project we just discussed. And let me tell you, there's quite a lot of exciting stuff to talk about. But I had the great privilege and pleasure to meet with some of the engineers from the Met Office during a visit at their site in the city of Exeter in the UK in March 2025, and you'll be able to hear all about it in an episode later this season. Suffice to say that at the Met Office there is a lot of code like the one Duncan worked on, that is prototype or exploratory research, but they of course have a lot of production code as well. So how do you transition from one to the other? How different is research code from production code? Is it actually different? These and other questions were something I wanted to explore with Duncan in the second half of our conversation. What I want to move to next in our conversation is your experience, how you think that research software and the software that you write in a private company can be different, or are they different in your experience, or are there different ways that people approach this?
I think, yes, I might start from longevity, I suppose. As a professional software developer working generally commercially, there are two modes of working. One is we're experimenting with whether an idea will gain traction in a market.
Right, sort of like a proof of concept that we're going to...
A proof of concept sort of thing, yes. And in those cases, we need to focus on productivity of our code. We don't want the code to slow us down. We don't want to get bogged down in it. But at the same time, we may care less about the ultimate quality than getting something into the market to discover whether the market likes it.
Right.
But then at some point where we believe we have a thing that is going to support us, is worth continuing to build, then we need to double down on quality to make sure that we have something we can live with for a long time.
And how does this manifest itself? So I mean the private sector, so the doubling down on quality.
I suppose
what's changing? Sounds like a gear change you're describing.
It's probably just in our fastidiousness, in the testing, in how much we care about the software quality, how much the internal quality of the software matches our models of the world, those sort of things. Because we want software that's easy to change, but if we change it, we know we haven't broken it. So a test-driven development, for example, is a way that helps us achieve both those things. I tend to see academic software written by researchers, as more of that exploration side of things than that extraction side of things. So we are more interested when we're working in data science, maybe, about the answers we're getting. Are we getting the answers we want, rather than can we change the software later to answer other questions?
Okay.
In particular, I think Python notebooks are really interesting because
in what way?
They are this weird form of experimentation where what you get out depends on the order in which you've asked the questions. So like we have a notebook where we say there's this cell, like we could run cell 1 and then we could run cell 7, and sometimes running cell 7 will change the results we get from cell 1 because there's state behind this whole thing.
Yeah.
They're very good ways of experimenting with a system, but they are not a good way of developing a reliable system, I think, because of this problem.
There are two schools actually of thought about Jupyter notebooks. So the one it's for experimentation and experimentation only, but there are also people who think that you can actually develop products with it. So are you saying that it's more problematic to do that with Jupyter Notebook? Or can you think of cases where this might actually work as a product?
So in my experience, they are very good at, if you want to use them either to, as you say, just get an answer to a question, or to allow you to play with the technology that is underlying them. So we've got a library of things that we then expose to a Jupyter Notebook. For example, Dask is a library. You can run up Dask within a Jupyter Notebook. You can start a scheduler, you can connect it, and you can load up data, and you can run those things within a Jupyter Notebook. That's a fantastic way of using Dask, but I don't think it would be a fantastic way of developing Dask. because
Okay.
Dask as a library, as an infrastructure, as a set of things, is going to need separate tests. It's going to need people running continuous integration servers to make sure that they haven't broken things and so on. And those are not things that naturally occur in Jupyter Notebooks. I did find a way of testing Jupyter Notebooks, which is interesting, because we were publishing our results as a Jupyter Notebook fundamentally. We wanted to know that this Jupyter Notebook was going to continue to give the output that we said it was. And so there, I can't remember the name of it, but there is a sort of test framework built into a Jupyter Notebook that allows you to say, run tests as part of a notebook and show. So for example, if we were to make a calculation and we might write a notebook to demonstrate a thing and say the answer is 42, and then our users come along and they run this notebook and the answer turns out to them to be 37. And you go, oh, well, that's because you had a different version of the libraries, or your data set was slightly different, or the time was different, or whatever. What actually you want to do is say, here, look, when I ran it, it was 42. And when you ran it, it's also 42. Or we show that there is a difference between the time that you ran this notebook and the time I ran this notebook.
Okay.
Sort of like a little cross-fertilization of engineering and demonstration, I suppose.
So you mentioned there are two kind of broad categories. So one which is sort of the exploration, the proof of concept, we are developing something new, we want to test this out. Then there's the extraction, the longevity, etc. of it. I guess that the project at the Met Office falls into the former category of the exploratory one. But quality plays a role in the exploratory phase as well. So how did you deal with that?
I think as a professional software engineer rather than a professional scientist, one of my jobs is to judge the chances of me messing something up. But there's a difference between the chances of me messing something up and the chances of a team messing something up, and whether if I mess something up, if I break something, it will come home to roost and I'll notice, or it will live there forever.
Okay.
And so I'm quite used to this sort of test-driven development cycle where we write tests to show that the code does what we expect it to do. When we're in the exploratory phase, we don't necessarily know what we want the code to do, and so we may well write fewer tests. But once we know what the code wants to do, we want the code to do, then at that point we might write tests, so it may be a bit later. But in particular, it may be early if it's the sort of thing we know we are likely to get wrong. And again, maybe that's some of the low-level things. If I'm writing some low-level code, I might say, well, I want to write a test to show that I haven't messed this up, because it's the sort of thing I often do get wrong. But if it's in the exploratory phase, I think there is less of that is important. Certainly, we wouldn't maybe have the sort of same acceptance test that we might have for commercial software. So it's commercial software, somebody will come to us and say, we think the software should do this. We'll say, okay, we'll write a test that shows at the high level that it does that, and then we'll write lower tests lower down that show the individual components that we've written to make it do that thing. I think when we're exploring, we very rarely write those acceptance level tests, because we'll know it when we see it. But we may well write some of the unit tests that show that individual components do the right thing.
Oh, right. Okay. I mean, you alluded to that already. Does that then change your approach to test-driven development? You mentioned that sometimes you simply can't do that because we don't know actually what it is we're going to write.
Yes. So I think we are way less likely to have acceptance tests for exploratory code. Because in the end, if a customer asks us to do a thing on a commercial software project, we are reasonably certain that we're going to be able to do that with this software. So we'll write a test that shows that it will work, what it will look like when it works, and then we will go and do that work. And then the acceptance test will be there not only to prove that it works, but to prove that in 6 months' time we haven't broken it, or if a customer asks for a feature that contradicts this one, that we'll know that they do contradict because the acceptance tests for this piece of code are broken by this other piece of code.
Right.
In exploratory programming, in the early, as you say, in the early days, we often don't know whether we can do a thing at all. So it's often pointless to write acceptance tests. The question is, how good could we make this? Will this work at all? And so, yes, the acceptance tests probably are certainly are, to me, a lot less important. But the lower level tests of, if I was writing matrix multiplication, for example, if that didn't exist, I would be writing tests for matrix multiplication if I needed it in my software, because that would be a thing that I could easily get wrong. And if I have got it wrong, then everything else is moot.
Indeed, exactly. The thing is that with research software, it's often a little bit like what I have seen in the private sector as well. Right. So because we are talking about the idealized version in the private sector a little bit, where we say, OK, we go from the proof of concept and then we decide, yeah, we want that thing. And then we build it from scratch. I have seen it. I'm sure you have too, that, we have a proof of concept that works. So let's put it out to the customer as a product. So that happens in research too, maybe not consciously, but we develop a piece of software for research, let's say a climate model, of some kind, and it proves to be actually very valuable to other researchers as well. So it then gets public GitHub project or GitLab project, and then it gets used by other people. For instance, libraries like scikit-learn started their journey like this, right? It is something that was useful at some stage, and then it became a big thing. So how do you manage then that transition of having something that doesn't need really acceptance testing because in this kind of funny proof of concept stage to actually we do need acceptance testing now because we find that it's actually a product?
I think lots of really interesting software goes through that stage, doesn't it? I've recently been working with a chap called Stefan Janssen, who has written an AI plugin for a development environment, just really to scratch an itch for himself. So he wrote it with the assistance of AI because he didn't really know how to write one of these. So he asked AI how to write it, and then it gave him some clues. But what he has now is becoming popular, but doesn't really have an acceptance test because he only wrote it for himself. And to some extent in the early days, that doesn't matter. Early adopters, are good at judging whether the quality of the thing is good enough for them. This doesn't work, but it doesn't matter that it doesn't work because I gain enough value out of it.
Yeah.
And there will be, if you're lucky, a large enough constituency to keep a project running of people who will overlook the shoddiness for the gains. If that doesn't happen, then we don't have a long-lived project and everything is fine. Like Stefan can continue to use his thing and nobody else will. But if he wants to continue, if this is going to become a successful project, what's the phrase? Crossing the chasm. It has to go from the early adopters into the mainstream. The mainstream need documentation. The mainstream need manuals. The mainstream need it to work. And so I think lots of projects go from this exploratory phase to engineers becoming involved, or the person that invented them having to engineer them better.
Yeah.
And often that's a dangerous phase for a project. We all saw what happened to Twitter, for example. Like Twitter went from this thing that was used by some people to this thing that didn't stay up because it hadn't been engineered for millions, billions of people across the globe. And some projects fail at that point because they can't be made into a thing or they are rewritten completely. So we know that we're now in the market. So we say, okay, we have a thing that will work in the market. We are going to keep that running. But in the meantime, we're going to go and do a new one.
Yeah.
Or we're going to take the thing we've got. We believe it is solvable, salvageable. If we add some tests to it, if we refactor it, if we change its internal design now to be better for the job we know it needs to do. Sometimes we change the language. Sometimes we just bring in a team of people whose job it is to take early experimenter code and make huge global megacorp code out of it. And yes, I think you're foolish to over-engineer a project before you know it's got product market fit, before you know it's going to be successful.
Yeah.
And so I don't, for projects that simply live as IPython notebooks, Jupyter notebooks, it's not a judgment. They are sitting in that early stage rather than having been engineered, but that's a completely rational economic decision.
At some stage, when you have to bridge that chasm, as you said, then, something needs to happen. So I think the good case, what I'm hearing is that early adopters, they're probably more willing to accept, as you say, the shoddiness of a non-product prototype, which is, where we write things quickly in order to prove a point. And it kind of evolves gradually into this product stage, or something serious needs to happen when we say, okay, yeah, this is ready and it needs to be turned into a product, in which case we need to bring in people and actually overhaul it, sometimes even from scratch.
Most scientific software, most research software, I think, is that, though. It, in my experience, once it has answered the question it was set out to answer, it is not required to keep it running. I think we'd like it if other people were able to use it to replicate results, because that would be useful. And often, I think science is getting better at that, but often we don't publish all of our algorithm and all of our data in order to ensure that people can replicate our results.
No, but we're working on it.
Yes.
Okay. Well, thank you very much, Duncan. That was a very nice chat and very nice seeing you again. And I wish you all the best for the future.
Thank you. It's been a pleasure as usual.
Well, bridging the chasm, as Duncan said, that is the chasm between prototype and production-ready software, is something that many scientific software projects have to come to terms with. It's not an easy transition, that. Not least because, apart from the technical problems, there are other fundamental questions. Like, how can you get the necessary people to work on it and turn it into a sustainable product? In other words, how can you ensure the effort is funded even though the funding for the research project itself may have ended. Well, that's a whole episode in its own right, that one, so let's leave it at that for now. But before I leave, I'd like to highlight a few workshops and conferences that are coming up. I probably should have announced them a little bit sooner, because the conference season, as you may have noticed, is already in full swing. So here are a few events, by far not an exhaustive list, that are just around the corner from the time of recording. In mid-May, the 13th to the 15th of May to be precise, we have the annual Collaborations Workshop, organized by the Software Sustainability Institute in the UK. And this year the event will be held at the University of Stirling in Scotland. There is an interesting lineup of keynote speakers, and I don't know if places are still available, but it's worthwhile checking, of course. For those of you living in Northern Europe, there is the Nordic RSE conference in the Swedish city of Gothenburg or Göteborg, I'm not quite sure how to pronounce that, to look forward to. It'll be on the 20th and 21st of May. The city of Hamburg in Germany is hosting again the International Supercomputing Conference, as every year, and there will be, for the second time now, an RSE workshop for those of you working with high-performance computers, and the workshop will happen on the 13th of June. We shouldn't forget our friends who work in digital humanities. King's College in London are organizing a summer school for software engineering for digital humanities between the 30th of June and the 4th of July. And actually, I hope I'll have a chance to go there myself and talk to a few people. And finally, and I know it's a little bit early to make announcements for it yet, but there's the conference of the Society for Research Software Engineering in the UK in late summer. The reason I mention it now is that they need volunteers either for the conference itself or for reviewing submissions, and you can apply for it now. So take a look at their website to find out the details and deadlines. The conference itself, as I said, is still a little bit away. It's between the 9th and 11th of September and will be hosted in Coventry at the University of Warwick this year. And you find all the links, of course, in the show notes as per usual. Well, next week we're going to talk about some really hot stuff, volcanoes, and my guest then will be John Stevenson. And I hope you'll tune in. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.